topic that I decided to work on for this presentation was parametric curves, which essentially what they are is a point given certain location on a plane, and that location is determined by certain equations. And as the equations change, the point moves. And when the point moves, more points are plotted, and it creates a general curve. And how I got interested in this, essentially, was from this object.
Hey, Joe, can I request turn the lights off so
Sure.
you can see things better?
And this is a 3D asteroid, basically. I think we're all kind of familiar with this form. And this rotatable object got me thinking, how do I make those curves without using little segments? How do I make them continuous? So I decided to work on essentially just simple curves at first. Objects like this asteroid again, only two-dimensional. And then going on to broader things like spirals. And then eventually I could experiment with more complicated images like this. All of these are rotatable objects, meaning you can manipulate them on a 3D interface. Although these things are basically mathematical, they're kind of aesthetically pleasing, you can make them into beautiful compositions. So I kind of experimented with that as well. So different ways of intersecting parametric curves creates, in my opinion, really beautiful images. Different objects that are rotated around each other in 90 degrees. Basically, that's what it is. It gets the general idea. Through a lot of experimentation.
It's called Geometry and Architecture, and basically my project has three main components. It has a photography component where I took black and white pictures of the IMAX theater, a 3D model which is rough but it sort of gets the viewer a feel of what it looks like and it can be manipulated, and two interviews, one with Chris Rowe, who's an architecture teacher. And basically this is the IMAX theater. Some information about it is it's one of the smallest IMAX theaters in the world. It had many architectural setbacks. It had to be built entirely on top of water. And this one, actually, I got an interview with the guy who designed it, and his name is Larry Donald Kilmer. Here are just some construction pictures that he gave to me. As you can see, the things are entirely on top of water. And what's significant about this in particular is that they built it, you see the seats that are there, and they built it entirely around that. And he also in the interview explained a lot about a sort of a curvilinear geometry and with people's focal lengths and just their vision. Basically, I also took some pictures. If you would like to look right here, this was a minor part. These are some black and white pictures that I took of the IMAX. Sort of a little bit more visually compelling, like not necessarily right at it. Alright, this is my 3D model. I inputted some pictures on Geometry Sketchpad. It's basically rough, but I plotted it on a 3D interface, and I used the X, the Y, and the Z axis. As you can see, this somewhat resembles it. On the next slide, you can see it better. This is a bird's eye view. The sidewalk, the parking area, and the ocean, which is right nearby. And this, if you want to compare just how it looks in real life to the model. Although it is rough, it resembles it pretty well. Okay, my interviews were filmed by Nick Morgan, who's another geometry student. here at CA. This is just a blueprint, and that right up there is a 3D model just to scale of another project he did, and those are the fabrics that he used for an office building. And what's sort of significant about the blueprints is that it's not available to the public, and I was one of the few people who could get it. Basically, Chris Rowe, as you know, he's an architecture teacher here. He also teaches sculpture, problems in architecture, just how you could connect architecture and geometry, and just get us a feel of the course. Larry Donald Kilmer, he works for the Genzer architecture firm, and he has worked on many different projects. He specializes in theaters and museums, and this project he enjoyed the most. And the way I found out about him, actually, he did a presentation to at my old. Like I said, this is the sidewalk. Up there to the right is the parking area. That's the ocean, and that's a gate outside the ocean. And if you want to just manipulate it a little bit, right there. That's if you're looking directly at it. If you want to. It's another view. And just to give you a feel of how many points, like I said, I pointed a point on the x-axis, y-axis, and z-axis, and then I hid them. This is basically all the different points that I plotted.
Mr. Larrabee likes things like
I
this.
do.
To show all the hidden.
Yeah, and it took, I mean, it took a lot of time, but I enjoyed the result, and hope you do.
Okay. I'm going to interrupt for a second. There are people trying to get in. Actually, Paxton, can you just indicate that they are welcome to come in? They have been reluctant to. In the corner. Just go into the resource on the. Yeah, please come in. Come in and as you please. No rush. By the way.
I'm just doing attendance.
Oh, you were doing attendance. I thought you wanted to, because she's one of our celebrated alumni of the demo day 2 years ago, Christiane Schalber.
Okay, and I'm good.
Anything else?
Yeah, mine was just really short.
Do you want to? Is this all?
Yeah.
Beautiful, absolutely.
The project is called Geometry and Architecture. I got into I was interested in architecture because my brother is also an architect, and a lot of my other family members are. And so I was able to observe his work and his processes, and it just really interested me, so I decided to do a project about it. So when designing my house, I knew that I wanted to go for a more modern style, and so I got a lot of books with examples of modern houses, and then incorporated some of the aspects of the houses that I liked into my design, which resulted in this and this. And I also did an interview with my brother, and he mentioned things like how, contrary to what a lot of people would believe or hope, a lot of the projects are based on cost and intentions of the client rather than the design will, I guess, of the architect. And he also said that as an architect, you're always looking around and taking in your surroundings and seeing what design aspects of other places you see you might want to incorporate later. And he also said that when you design a house or some sort of building for a client, you also get to know them really well. This is an example of, well, he's only designed one house because he's kind of just starting out, but he designed this house in Martha's Vineyard, and he described that as a barn vernacular kind of style, and he said that that was what he would be interested in pursuing later.
Any questions? Fabulous.
Myself in that kind of question-answer kind of situation. It was more of a conversation, and it was a lot easier because I already knew him, and I already had a sense of what he would answer to my questions, so it was easier than.
Beautiful. Fabulous. Yep. Up to go.
So I'm Grady Gund, and I did a project on Eratosthenes, who he was an ancient mathematician, and he did a whole bunch of things, like proving the world is round by, and he did this with this. He was in Alexandria, and no, he lived in Syene in Egypt, he lived in Syene, and he realized that the light from the sun shone directly down a well because Syene was directly below the Tropic of Cancer. So and then the light extended down to the end of the well, and he put a pole up in Alexandria where he worked as the librarian in the great library there. And so then he realized that since the angle the light hit the pole at was congruent to the angle where the sun and the pole extended to the middle, because since sun's rays are parallel, we know that these are congruent by alternate interior angles. And so you can move if the pole goes up. It's still true. And besides doing this, I also, and there's chorus parts in it, like in real Greek plays, and so I recorded the chorus last night. There has to be someone who remembers something of mine.
You should begin searching for intelligent people.
I remember some of my proofs. I just need help from someone to fill in some of the details. My weary dead mind is not what it used to be. Wait, I thought I had to return to the underworld with you immediately.
The world needs your work. If you can find a way to recover them, including my poem, I will allow you to stay here for a time.
I think I can find a way to do that.
I knew I recognized you from somewhere. I was your scribe and bookkeeper at 13. I wrote some of your most famous documents, like the original Seed. You needed to know about prime numbers for something involving star mapping, so I wrote it all out for you.
I knew there had to be someone who knew my works. Do you remember much?
I do have a fine memory. I think I could give you a hand with some details.
That is fantastic. Not all my work is lost. Let us get to work.
I am a ghost as well, and like you, cannot write.
We must find a living person then.
That will work quite well. I shall lend you my wand so you can visit worthy people in their sleep and inspire them.
We can pour our combined knowledge of my works into their heads, and then when morning visits them, they will begin to write.
I'm Eugene Ha, and I did a project on geometric puzzles, and most of these puzzles were either really ancient or made by Sam Lloyd. So how I got interested was when we first learned about the bridges of Königsberg in geometry class. And so I started off with really simple puzzles, like this puzzle where you have to connect the 9 dots with only 4 segments. So this project mostly consisted of trial and error. So it all depended on how much time I spent. So this is the solution for the first one. And as I got deeper into it, Mr. Tezal let me borrow one of the books of his, and so it consisted of numerous puzzles like this one. This is a puzzle where you have to you have to create 2 Greek crosses within this one. So a definition, in order for me to go through this, was I had to first define what a Greek cross was. It was 5 squares practically latched onto each other. So this is the solution I got, and if you put it right here, it'll correspond.
So the yellow area reassembled creates that yellow
Yes.
cross? Okay.
Without rotation.
Okay.
So this would go here, and this would be from here. This would be from here. This would be from here, and with resembled, it will the area will correspond to the red area. Yeah, this one took me quite a while, but it was worth it. Other puzzles include this kind of puzzle. Oh, this was similar to Bridges of Königsberg, just that it was actually possible. You would have to go through each point, which was practically a town, and you had to visit each town once without going through the same town twice, and you had to start here and end up there. So my puzzle, also there's another element to my puzzle, which is the Rubik's Cube, and I will be displaying that during the science fair.
Show this, please.
And so this is the solution, the bicycle will travel.
Just traveling on this really convoluted path. A lot of us actually, I never showed you how to do this. Can you actually show all hidden? Make Mr. Larrabee happy, and we'll also see how he tweaked this display. Show all hidden. You're gonna notice it's traveling on a really convoluted polygon. So you could you could have an object animated on a perimeter of a polygon. That's how he's doing the trick.
United States of America, 15th rank in the entire world. And so he would go around making chess puzzles, and this was one of the versions of his chess puzzles. You had to place 8 queens on a chessboard so that none of them can kill each other. And this is the solution.
This puzzle has about like 92, 96 solutions. Gauss failed in the process. He got like 82 of them or something. He couldn't get the last 14. It was only once computers were invented, people were able to figure all of them out.
Yeah.
Beautiful. Yeah, anything
That's
else?
all.
I'm Sarah Thornton.
I'm Natalie Salzman.
And we did a lot of 3D stuff in Geometer's Sketchpad. And the things that we did that were the same were plotting the platonic solids, and I think we did 10 or 9 of the 13 Archimedean solids.
Okay. Again, if you want the lights off, and actually don't block the lights so that we can see. And if you're gonna show stuff, let's have somebody push the light switch off, please. Cool.
Okay, so first, we started using the old platonic solid system, or the old 3D
So
system.
this is relevant.
This is the one, by the way, just historically, this is the one that Nick Green basically developed. This is the one that we've been working all last year.
And you create these to look 3D by planting them on an ellipse. So this is the ellipse you have here, and the points will travel as you animate them to look like it's spinning around.
See, but the problem is it's not real, so it can get
Distorted really easily, and you can only spin it in one direction. So it's not truly in 3D. We're just creating an illusion. So those are the 5 platonic solids.
Then the math department created a new new 3D system called a 3D interface.
And to use this, you have to find the coordinates for each of the shapes you want to create, and you plot them, determining the location based on the X, Y, and Z axis for one individual point. So that's the octahedron.
This is the icosahedron. And basically this little slider just enlarges it.
So you can get it whatever size you want. And so this will spin in all different directions.
Those are all the coordinates.
And in order to get this, you multiply the original coordinate length times the distance between P and O in this case, so that as you move P, it will expand, so the distance of the points and the separate distances will increase.
Okay.
Then we started experimenting with Archimedean solids. To do mine, I basically truncated the sides of platonic solids, and Sarah did differently. She actually plotted the coordinates.
Yeah, I continued with the plotting of the coordinates. So Natalie's will only work for the Archimedean solids that you create by truncating, and mine will work for all of them when you figure out the equations for the coordinates that you need to use.
Where did you find the coordinates of the
I found them on
Archimedean?
the internet, and one of the great resources was Wikipedia,
Wikipedia?
and that had everything. Sometimes it was really confusing, actually, the terminology they used, but for the most part I was able to figure it out. So it takes... Do you want me to open mine up?
What?
Do we have them all here? Do you want me to
Yes,
open mine up?
all
Yeah,
of these
sure.
are.
So I'm just showing, this is the truncators.
Do you want?
Yeah.
Okay.
And make sure to also show the chemical stuff like the
Oh, sure.
at one point. And actually, maybe show a couple of things, but let's really move to the chemistry given the time frame.
Okay, do you want me to move on?
You're welcome. Like show actually a couple of your regular Archimedean stuff, but then
Alright, this is one of...
Okay, after I built all the platonic solids, I also played around with duality. So at first I built a cube, and then inside the cube I also did the octahedron. And so you can see how to do that. I also did the dodecahedron and icosahedron. So I first built the icosahedron and then the dodecahedron.
very good. Moving on.
I started with the basic knowledge that most people know of what makes up a water molecule, which is one oxygen and two hydrogens that bond together at a typically about 109.5, I think it's 109.47 degree angle. So that angle right in there. And there's a whole bunch of confusing distances that I'm not going to drill you with in nanometers that I sort of changed so that it fits in here. And they end up, as they bond, creating tetrahedral structures just based on sort of a whole bunch of deep chemistry that I wasn't able to learn exactly why. But, so those change. And then, in order to do this, we had to build even more tetrahedrons. So these are the basic, you start with the tetrahedron and make the oxygen, which is, in this case, the origin is also the center of the tetrahedron. And so that's that. I think, that's
Yeah.
about it.
Fabulous.
My name is Joe Byrne, and my project is Mercator and geometry. And Mercator was a cartographer back in the 1500s who had to deal with a problem, and the problem was that the Earth was round. And to create a flat wall map, he had to project the sphere of the Earth onto a flat surface, and also at the same time minimize the amount of distortion so that Alaska and Greenland didn't look gigantic and Ecuador didn't look tiny. And so basically there's a lot of methods to doing this, and the one that he devised, and the reason why it's famous, is because this is a sphere that I created, or that Slim created on Jetpad, and then on Sketchpad that I remodeled. And this is the method that he used. So this is the sphere, and what he did was, you can imagine that he had the sphere and he wrapped a cylinder piece of paper around it, basically. And so the equator imprinted itself on the cylinder, and then as you get farther away from the equator, the imprints of the latitude get farther and farther apart from each other, so that the more distortion of scale occurred closer to the pole. And basically that was his method of devising it. and in comparison to other things that other people did, especially things.
Put a ray there just to make it clear, but you could show either that or your own. Both
Okay.
of them are fine.
And so this is another method that people use called azimuthal. I don't know what that means, but basically it's ray going straight from the center of the Earth and imprinting itself on the flat wall map that would be at the center on the North Pole or the South Pole. And so the map would look like a circle with the center being the North Pole.
Yeah, rotate it so we can see. It's hard to see when it's stationary. Do you see how a point on the globe is projected on that flat surface? So that way you could point by point plot every point on the one of the hemispheres, obviously, to that flat sheet. So this is one projection, and what he's saying is Mercator is different, right? Mercator is
Right.
with the cylindrical
He
wrap
revolutionized the cartography industry.
with that method.
So that's that.
I'm Annalisa Cooper, and this is my project titled Penrose Tiles. Katie also did a project about Penrose Tiles, but mine adds the sort of artistic aspect that I tried to knit them. So, as Katie explained, I have a little blurb here about Penrose Tiles. They were developed by Roger Penrose, as she said, in 1974. She explained about two types. There's the rhombus, there's the two rhombuses, and then there's the kite and dart. And as you can see, I picked the kite and dart version. This is what version of what the quilt looks like, but it has, just to show, because one of the rules is that the arcs need to align, sort of in this loop pattern here. So this is my original sketchpad version, just to show that my design worked with the rules. And then this is the version that sort of looks more like what you're looking at. This was how I figured out how to do one of the tiles. I didn't have enough room on my poster to put how I figured out this one also. But basically, you measure each side. First you get what's called a gauge swatch, which is basically a square. That tells you how many stitches you have per inch, or in my case per centimeter. Then of course you measure each side, and so then you know how many stitches you need on each side. Then you would measure sort of a span piece here and realize how many stitches you would need to decrease over this amount of time by measuring how many you need here and how many you need here. And then you would distribute them evenly. Same for this part. So after knitting many, many swatches, I finally came out with a pattern that worked, and that makes this, and another pattern that worked, and that makes this. So then I basically sewed them together in this pattern, and this is most of what I have.
So I'm Nell Robinson, and I did a project about op art. It started when we, at the beginning of the year, had to create our own op art, and I created a hand, and that was where I got interested in op art. So I decided to make animated op art for my final project. So to start, I just started animating stuff so that I got to feel the animation like this eye, which kind of blinks. And then I moved on to animating op art, which this is just a very basic thing with a square where the internal squares move. And then I progressed to making a clock that actually works. I mean, it's not on the time of a clock, but it does move as a clock would, just faster.
Colors change as it moves.
Yes, the colors change as well. That was cool. And then I started to work on my final project, which was going to be a circus scene composed of a juggling clown and a Ferris wheel. So
Figure this.
I made the juggling clown.
Can you turn your computer screen just for a minute?
So I made a juggling clown. He changes color as well. And then I also made the Ferris wheel with little smiling people that spin around. And then I put them all together to create my final project.
All we need is some circus
Which-
music.
Yes,
Da-da-da-da.
I know. I did look for circus music, which I could not find. It was tragic. But, so, that was my final project.
My name's Amanda. My project is geometric embroidery, needlework, it's curved stitching and other garments. Basically, I made a dress and a bag, and I curve stitch on the bag like this. And basically, curve stitching is just lines that form curves and other cool stuff. And you use like angles and all, and a lot of polygons. And for my bag, I had to use pattern, and I had to measure a lot of stuff, and also for my dress. And I made a 3D model of.
At this point, Christiane must be in tears. She was the first person.
I'm Paxton Krasinski, and I did a project about pagodas. Buddhism is a big part of my life, and the pagoda is a structure that's built in the center of Buddhist temples and is a big power, actually a power structure for places of meditation. The pagoda originated in India with Buddhism and evolved throughout Japan and Thailand and Korea and China as the religion spread, and eventually became the stupa, which is a building that is created on the remains of teachers. There was a stupa that was recently built in Colorado at the Rocky Mountain Shambhala Center, which I actually helped work on, which is about 200 feet tall, and it took 13 years to make. This model is a model of a Japanese pagoda, much like this one here. I couldn't actually make curvatures of the eaves with plasterboard, but it's a fairly resembling creation. I also made a GSP model of the pagoda to the same specifications as the board one and to the one in the picture.
Unbelievable.
My name is Fanny Watkinson, and I did Cantor's Infinity. So, as a quick overview, Cantor was a man who was born in Russia and then moved to Germany. And he essentially proved that there's a hierarchy of infinities, meaning that some infinities are greater than others, or have more members in them. And in this time period that he really, like, people were like, infinity is such a scary thing, don't go near it, don't touch it. And he was infatuated by it. So he really, really worked with these abstract concepts to prove this. He worked with a one-to-one correspondence. So I'm going to draw a picture. If you have, let's say, okay, all right, I'm not going to use the board. You have 5 fingers. But let's say you're trying to see and measure something that has 10, but your system only works in 5. So you don't know that, let's say that if your 10 fingers is bigger than your 5 fingers. So what he did was he said if you can match each number up 1-to-1 and there's still more left over, then that set is greater or bigger than the original one.
Yeah.
So he used this one-to-one correspondence to prove that the natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and on, and the integers are equal, or have the same number, the same cardinality, the same number of members in them. And he ordered them like this, which is his famous diagonalization proof. So we essentially put 1 over 1, 2 over 1. All right, I'm going to use this. It's all apart because it's going to be big.
Maybe just the final results. Those
The final
details we
results?
will not be able
Okay,
to.
so he had these proofs, And he essentially proved that the rational numbers could be put into one-to-one correspondence with the natural numbers, so they also had the cardinality of Aleph Null. And so then he set about attacking the real numbers. And the real numbers include everything. And he worked with the interval from 0 to 1. And so he tried to put the natural numbers in a one-to-one correspondence with the real numbers in 0 through 1. He discovered, it's amazing proof, he discovered that there are actually a ton more real numbers in that one interval than there are natural numbers to be matched with. So he proved that the real numbers have a greater infinity, or greater cardinality, than the natural numbers, and he called this number Aleph 1, which is that same thing with the little subscript 1. So then, these were, heart-wrenching, breakthroughs for everyone, every mathematician in this field at the time.
About your process, how did you crack things down in terms of proofs and so forth?
I found a great website that it was all about set theory, and so I read a whole lot and got a whole lot of information on sets and what that, incorporates, and figured out all of the logic around that. And that built up and built up and built up until I got to some of the more complex stuff. And some of these proofs are like, I look at them and I absolutely have no idea what they're talking about. But if you break them down and you figure out what each symbol means, you can kind of construct kind of an English translation of what these are trying to say. So that's how I went about it, just building up the level of intensity.
Beautiful.
So, Drew Kelly, Sacred Geometry. Alright, so these are just arches. Let's see. So that's basically all those are. Then these are like quatrefoils, which are basically smaller parts of designs for windows. Say that's an arch. Another type of arch.
Look at the complexity that is hidden. I mean, the final product is very innocent. We see this all the time, all over the place. Look at the complexity of that. The number of intersection of triangles and circles, and he cracked this down. He figured out how to do this. I mean, quite unbelievable.
There's another quatrefoil. And then this thing, I don't really know what that is. But
Beautiful. This I haven't seen actually yet.
yeah, this thing took a really long time to build, but it was just basically a lot of smaller arches and quatrefoils and trefoils rotated around. Let's see. Yeah, there's that.
I love the name of this. What is this?
This is the flower of life, and there's like
Flower
a
of
cult
life.
for this thing.
Oh, I love
And
this.
here's Islamic design. So, that took a while to figure out actually. And here's just like Kepler's thing with the platonic souls
Yeah.
and the planets.
You give it a spin so we can see.
And here's just another. Here's just another window.
Look at that detail. I mean, the amount of detail in that.
Alright.
Name, type.
Danielle Searles and non-Euclidean ceramics. So what I did is I made 2 vases, and one with tessellations and one with more like 2 colorable like theory. This is the tessellation one that I did, and I wanted to make tessellations on a 3D surface with interesting curves and stuff. So the bottom, obviously, I wanted to make a lot wider and then get narrow at the top and see how the tessellations kind of reacted. And so I had to come up with a grid system where I had to measure the length of this and the length of the bottom around, and I ended up dividing it by 5 sections, so there was 25 altogether. And so I started at the top, and so it starts as, you can see that they're regular squares. And then what I did is I measured the top of the rim and duplicated it down here vertically and created a horizontal line across. And I guess one continuous line throughout the entire vase, except it can't intersect in an uneven number, so you can't have 3 or 5 or 7 intersections at one point, but you can have 2 or 4, which works. And 2 colorability is once I wanted to prove to see if it would work on a 3D surface, because it works on a 2D surface, and we weren't sure whether it worked or not. So what I did is I just did the same thing that I had actually practiced on paper for a while, and it ended up working, where you can see that there's no specific point where there's like 2 where they, I guess, are side by side. So like the yellow here, there isn't like a yellow right here, I guess. And
Good to go.
I'm Nick Charcola, and I did 2-dimensional, 3-dimensional trajectories with a cannonball. And basically, I'm going to start with the 2-dimensional stuff. So start with initial projectile motion. Right. And what I did here was you have your cannon right here, right? And if you move it up and down, you aim it. And you can, if you want to show the steps and show the locus, this is what will happen. And if you expand it, it'll do this, and then you move it up and down, that's where the cannonball will go.
Is that Concord Academy you're shooting at?
And so you press the fire cannon button, I guess, and that's what the cannon does. It goes where the end of this will go. And if you want it to go farther, you can do that. So yeah, so you can fire the cannon, you can move it up and down.
That's
This is just initial. You can't move the point of the cannon because this is at the origin is where it fires from. Move the point where the cannon fires. And again, if you show steps and show the locus, this is exactly where it's going to go. So if you want to move, if you were able to move where you were firing from, you move from there and then you fire the cannon there. So this is the 2-dimensional stuff. It's pretty straightforward. So the monkey starts falling and the cannon starts firing at the exact same point, and you want to make it hit, right? And say you didn't. No, that's not what I did. Say you didn't have this aiming aid that I had here. Say that you didn't know how to aim it. You just kind of guessed. And say you went here and you fired the cannon, and the monkey will fall at the same time. You miss by a lot because you're not aiming directly at it. The secret to how actually to solve this problem is that I made this little aiming aid, and if you have this exactly aiming at the monkey's head, say, and you fire in slow motion, notice where the cannonball hits. It'll hit exactly the monkey's head. This is just to show how many parameters it takes to make just this many points. And now it's just kind of an introduction to 3-dimensional. This is firing a cannon at a castle from the origin, and you fire the cannon. And the way to aim it is if you show the steps and fire both cannons at the same time, and you make it so they hit each other in midair. But the important part is that they're both firing at the exact same time. They're both starting. I mean, you could fire this one by itself or this one by itself, and it would make a difference. I just made it so they stopped pretty much. I mean, where it says X right there, and I guess when it gets high enough, you just want to fire the cannon, and you always miss because you can't hit it. But this is what's actually happening here. Is if you want to show the locus of each one, this is actually what it's doing, and it's just. I still haven't been able to hit it, which is annoying me, but
I'm Mallet, and I am going to be talking to you guys about non-Euclidean geometry, specifically hyperbolic geometry. Now, in a minute I'm going to show you this really awesome lab that I made, but before that I just want to talk about hyperbolic geometry itself for a little while. It was discovered by Carl Friedrich Gauss in the 19th century when he was trying to prove that triangles must at infinity. Let us say on the edge of the disk, you can make a triangle with 0-degree angles. And this segment, the segment FG, you can't see because it's at infinity, and infinity, like, it goes on forever, so that you wouldn't be able to see it. But you can still Sketchpad is not able to display it, but you can still measure the angle Sierpinski triangle. Whoa, what happened there? Anyway, you can construct it the same way that you would a Euclidean Sierpinski triangle, and I like it because hyperbolic triangles, you can make them into some really weird and awesome shapes, like this, and you can't do this in Euclidean geometry because Euclidean triangles are lame. But anyway, that you create from an iteration, like all of these little triangles are congruent if they're on the same iteration, the same level of iteration. And not only that, but every single triangle in a Euclidean Sierpinski triangle is similar. Now, in a hyperbolic Sierpinski triangle, even if they're on the same iteration, they're not similar at all. Not necessarily, anyway. They can.
I'm Alex Miller, and I'm going to be continuing on this topic of non-Euclidean geometry with the well-rounded cousin of Euclidean and hyperbolic geometry, spherical geometry. Now, this was discovered about the same time by Gauss and two other, Lobachevsky and another Polish guy, whose name escapes me. It was developed at the same time as hyperbolic geometry because it's the exact opposite, in that rather than having an infinite number of parallel lines, there are no parallel lines. And I'm going to give an example right now on this wonderful thing called the Leonard sphere, which is basically what this is for hyperbolic or Euclidean geometry. So here we have a ruler. That's a normal ruler. Now, for spherical geometry, what's interesting is that lines are always going to be curved because it follows the curve of the Earth. So, and two angles. And one wonderful thing about this is that it can't be created in Euclidean geometry because it just looks like a straight line.
I'm Bonnie Cow, and I did my project on fractals. And just to refresh your memory, fractals are self-similar objects, and they're constructed recursively. Since you guys have already done the Sierpinski triangle and the hypnospiral, I'll start with the snowflake. Some of you may have already done this, but it starts out as it's supposed to start as a triangle, and then you add on little triangles all around. And the interesting thing about this is that the area is finite, but the perimeter is infinite, because these can keep going more and more.
Okay, I want to make sure that that remark does not go without its impact. Did you hear it? Repeat it one more time loudly and clearly. What happened again?
The area is finite, but the perimeter is infinite.
The area is finite, meaning this thing will never blow out of the page, that you can believe. But the perimeter is becoming so convoluted that the perimeter is actually going to become infinite. This would turn Euclid in his grave, right? And actually you might remember the discussion with David Mallet about the coast of Britain, etc. Very good?
With iterations, you can make it into a firm tree sort of thing. And all the little branches are similar to the original.
This is called a space-filling curve, kind of Watkinson territory. This is about how something becomes infinite in a process. Yeah?
This is the Pythagorean tree, which starts with the same shape that we did on a little lab to prove the Pythagorean theorem. And then with iterations, it is again self-similar, and it is another type of tree.
Yeah, the speeds are sometimes different than what you expected, yeah.
So the square, if you take one of these, one side of the cube, it will be a normal.
Jenna Troop, and I did a study on
chaos theory as it relates to many of the fractals Bonnie just showed you. Alright, so side Pascal's triangle. Alright, and so now we're going to go on to more detail. It's basically repeating itself just as Scripinski's triangle did in an octagon form. And itself similar throughout, almost sort of like the iterations, but not as an iteration. And so this is just sort of a statistical format of all of that. That's all.
Fabulous.
My name's Jason Gregg. My project's on reflection, optics, light, and here in my poster I give you examples using, they all incorporate parabolas, so once you understand that, you get the basics of reflection. My image up here is the inside of a reflector telescope. It shows how the image is refocused and redirected to the eyepiece. This right here shows you how an image is enlarged using a telescope and a parabola here.
I photocopied it a bunch of times, and then it was.
That looks really cool.
Yeah, thank you. Wow.
It's a project merging op art and
Is that thing on?
origami. Just keep.
Oh. Yeah, so each of these was made out of a different unit. So then, like, I think for like this one, these vertexes, I needed 12 of them, and I needed like 30 of these. And then I know for that star, it took 30 star modules, which then fit together, and it's a star. Whoa.
So your name, please.
Oh, Mac Oldenburg. I did origami and geometry. So I did a lot more traditional things. So everything's made out of one piece of paper, and so it doesn't. A lot of origami forms are like really organic, so you don't really see a lot of, like, you can recognize some shapes, like you can recognize triangles and like polygons, but like a lot of it is in the pattern of folds and in the layers. It's like when you're folding it, you recognize a lot of symmetry and similarity between the shapes, and when you unfold everything, like on the poster, you notice all the folds are left and you can see a lot of patterns created, and that's really where all the geometry works in. And a lot of people like are exploring this, like mathematicians and physicists, and there are all these programs that like can, using these weird mathematical theorems, can create amazing models of that are really complex. But basically these are just a bunch of the ones that I folded. Like this is similar to what Beth did, although this is one piece of paper. So when you unfold this, you see a lot of symmetry and a lot of different geometric shapes that made up this, and you only see like a little bit of what it actually is, because everything is buried in layers.
So my name is Nick Morgan, and for my geometry project I investigated the geometry of flowers. And this started out as an art project in which I would like draw botanical pictures, like with a mind to show the geometry, and then eventually it became more geometrical as I would take pictures of flowers and put them into GSP and measure the angles of the petals. And then I started to experiment with finding average angles and trying to replicate the structure of the flower petals with a formula. And so after doing that with just simple angles, like say, since 360 degrees is a circle, divided by 4 petals is 90 degrees, reflecting this 90 degree. Replicate the shape of the flower, as in this example. So, and I worked with GSP to make like a system where you could use sliders to change the tilt of the petals and the size, and also the number of petals. And so you can see also here I did the same thing. And then I would experiment.
Yep.
Hi, I'm Sammy Morse, and I looked at the work of Alexander Calder and his work on mobiles. Now, Alexander Calder, he was born in 1898, and he was the son of 2 artists, so he had an influence of art from an early age. Originally, he was going to be an engineer, but he gave up on that after a little while and merged the 2 ideas of art and engineering into his mobiles. Now, basically, the idea of a mobile is it's a 3-dimensional sculpture that moves but is not doesn't have any motors involved, so it's a very free-form movement. And so I was very interested in this, so I decided to try to make some of my own mobiles and study how the balance in them works. So as you can see here, there's two ways you have to balance the mobile. Firstly, you have to balance these so that they don't hang like this or like that. And then you have to balance this part of the mobile so that the rods holding them up don't wiggle too much. So firstly, I looked at how to balance this part of the mobile right here. And so I looked at three different shapes and how to balance them. I looked at triangles, circles, and quadrilaterals. And the circle was pretty easy because, well, the general idea was to find a point on the shape where all the area was equally balanced around it, and then it would be balanced. So for the circle, it was pretty easy. It was just the center point of the circle, and everything else was evenly spaced from that, so it was perfectly balanced. The triangle was a little more complicated. The idea was to create two medians of the triangle. I don't know if you can see right here. We have median number 1 and median number 2, excuse me. And where they intersect is the point of balance, because when you create one median, you're creating two triangles that have the exact same area. And when you create the other median, you're creating two more triangles that have the exact same area. Thus, when you hang it by that, this one doesn't work very well, it is balanced. The square was a little bit more complicated. To do that, you created first one diagonal, and then what you did, this created two triangles, and you found the center of balance for both of these triangles and connected them with one segment. Then what you do is you create the other diagonal and find the center of balance of the two other triangles and connect that with a segment. Where those segments intersect, the quad balances.
Christine Mayer, I did dualism with platonic solids and Archimedean solids. This is icosahedron, the outside line, and the inside you could see this golden rectangle in it. If you connect the vertex of each rectangle, you get a cosahedron, and I studied that in GSP Sketchpad. With the other ones, like this one, this is rhombi cuboctahedron, which I got it from Sarah Thornton, and I connected the midpoints of each face, and then I got some kind of shape inside, which is the line without the dotted lines, yeah. And each face was concave, so that was kind of interesting. And well, I created this truncated cube by first creating the cube and cutting and dialecting each side by 1/3 and 2/3, and then I connected the points and got this truncated cube. And then I got the center of each face and then connected them, and then that's the shape I got it inside. So
Now we see some former graduates of the demo day. Would you please kindly introduce yourselves and tell us what you think about the new products?
Well, I'm Grace Maskell, and these are gorgeous. And someone did Sudoku, and I think that's incredible because I would not have thought of to do something like that.
I'm Katie McNally, and I just think like these projects, just from what I've seen in the past few minutes, they're really original. A lot of them aren't like we had last year, so it's really cool.
And we should actually focus on the works inspired by Grace at this point, some op art works as we can see.
Those are beautiful.
And then we should notice that Ilan Stai's project on architectural interviews was actually inspired by Katie McNally's